In 3.1, we talked about the definition of a derivative, and that was using the limit definition. The limit as h goes to 0 of f of x plus h minus f of x over h. That's the long limit definition in 3.1, and that really is what a derivative is defined as. But if we had to find derivatives that way all the time, calculus would be a very, very, very long course. Luckily, there are some shortcuts that allow us to find derivatives more quickly. And the biggest one in 3.2 starts with this one is the power rule. And this is a way to find a derivative without having to plug into that big long limit. But you get the same answer either way. So what it says is that if I have f of x equals x to the n, where n is a number, and x is the variable, when I take the derivative of x to the n, the derivative says I take the n and multiply it in front, and then I take 1 away from the power. So that's all the power really says. The derivative of a function takes the power, and it becomes a coefficient, it multiplies in front, and you take 1 away from the power. And this power rule works for n when it's any integer, it's actually any number. If you put any real number in there for n, you can find the derivative using the power rule. So let's look at a couple examples of how we do this. The first one here is x cubed. Find the derivative of f of x equals x cubed. Well, we're going to use the power rule to do this instead of the limit definition. And what the power rule says is when you take the derivative, the number in front, in this case the number in front is the number 3, it multiplies in front of the x. And then the power the x is raised to gets subtracted by 1, and 3 minus 1 is 2. Really short and quick and sweet. Now the next one, b here, is the cube root of x squared. The trouble with b is it's not written as a power. So before I can find the derivative of b, I have to write that as a power of x. And x has to be in the numerator, it can't be in the bottom of a fraction. So the way you write a root and a power, the way we put this together, is we can rewrite f of x as x to the 2/3 power. Now we have x raised to a power. We can use the power rule to find the derivative. And what the power rule says is the 2/3 gets multiplied in front of the x, and I take 1 away from that power. So it's 2/3 x to the 2/3 minus 1. I have to take 1 away from that power. And when I take 1 away from 2/3, I get negative 1/3. Now just so you can see all the possible answers, you could have also written this a different way. Since the x to the 1/3 is on the bottom, or since the x to the 1/3 is a negative power, it's the negative 1/3, I can make it a positive 1/3 by putting it on the bottom. And 1/3 is the cube root. So here's another way I could have written the derivative. All of these three answers are acceptable. But notice how the power rule works regardless. Let's try this one here. C is x to the 1, f of x is 1 over x to the 8th. I can't use the power rule yet because x is in the denominator of a fraction. But to move x to the 8th to the numerator, I just have to make that power negative. So this is the same thing as x to the negative 8th. And now that that x is on the top of the fraction, I can use the power rule. Negative 8 is the power. It multiplies out front. And I take 1 away from that power. And so my derivative, that's f prime of x I just found. My derivative is negative 8x to negative 9, which is an okay way to write your answer. But just for full disclosure, this is the same thing as I could take that x to the 9th and move it to the bottom and make the negative power go away. So both of those answers that are in the boxes are perfectly acceptable. And the last one is a twist on b and c. I have the square root of x, and it's in the bottom. So the first thing I have to do is write the square root as a power. And the square root is x to the first power, second root. So that's x to the positive 1/2 when it's in the bottom. But I have to move it to the top to take the derivative. So to move it to the top, I write that as x to the negative 1/2. Now I can use the power rule. I see that I have x raised to a power. And so using that power rule, the negative 1/2 multiplies up front, and I subtract 1 from that power. So the derivative is negative 1/2 x to the negative 1/2 minus 1. Negative 1/2 minus 1 is negative 1/2. That's negative 3 over 2. So you get negative 1/2 x to the negative 3 over 2, which is an acceptable way to write the answer. But in the interest of full disclosure, this is the same thing as negative 1 over 2x to the positive 3/2. It made the negative disappear from the power. And you could also write x to the 3/2 as the square root of x cubed. And there are other ways you could simplify that as well, but these are kind of the more common ones. So here are 3 different answers. They all would work for part D. So the power rule is just, you write it as an x to a power, you take the power and multiply it in front, and subtract 1 from the power. And these are good ones to practice, because this stuff is the foundation of the other derivatives we'll find. You can use the power rule to find the derivative of a constant, too. But to do it, you have to think a little bit about what it means to be a constant. The power rule works when powers of x. But you'll notice f of x equals 7 has no powers of x. Well, 7 is the same thing as 7 times 1, and 1 is x to the 0 power. So that's the little trick that we play. We write constants as x to the 0 power. That number times 1 is that number times x to the 0 power. So when I find the derivative, the 0 gets multiplied out front. I take 1 away from that power. Well, 7 times 0 is 0. And 0 times anything is 0. 0 times x to the negative first is still 0. Now if you look at part B, you can do the exact same thing. It doesn't matter what the number is. Negative 2/3 is the same thing as negative 2/3 times 1, which is negative 2/3 x to the 0. So when I find the derivative, it's negative 2/3 times that 0 gets multiplied out front, x to the negative 1, and 0 times anything is 0, and 0 times x to the negative 1 is 0. Notice when I have constants, the derivative always turns out to be 0. That is not a coincidence. That's actually a truth. The derivative of a constant is 0. The rule. So if f of x equals c, where c is a constant. Now what I just wrote is c is an element of R. This is fancy math speak to say that c is a constant number. But you'll notice there's c. E means it's an element, or it lives in. R is the set of all real numbers. So this just says that if f of x is a number, any real number, well then the derivative of just a constant sitting all alone is always 0. And we've shown with 2 examples that was true there as well. Now that can get confused with the constant multiple rule. If it's just a constant all by itself, like the number 7, just a constant sitting there like the number 7, or the number negative 2/3, the derivative always works out to be 0. No variable appears. But if you have a constant times a function of x, then the constant doesn't go away. It just factors out. And this is the proof that they give in the book. They say, this says that if you can find the derivative of x and c is a constant, then the derivative of c times the function is the same thing as just take the derivative of the function and multiply by c. Well, this is what it means. We see that f of x is differentiable at x. So that means the derivative of f of x, and there's the limit from 3.1, exists. Well, if c is a constant, then if I tried to find the derivative of c times f of x, which is what the problem originally asked for, then I could put that in the limit definition. That's c times f of x plus h, minus c times f of x. Because notice I'm replacing f of x with c f of x. Well, when I do this, there's a constant in both those terms that I can factor out front. The limit as h goes to 0 of c times f of x plus h minus f of x over h. But this limit only has to do with h's, and that c isn't an h. So I can factor the c outside the limit. And since this derivative here is since this limit here is the derivative of f of x, you've proven that if there's a constant in front of your function, you can just multiply the constant times the derivative. So people get that mixed up with the derivative of a constant because this sounds similar. If it's just a number, the derivative is 0. But if I have a number times x's, the derivative, the 8 doesn't go away. For example, in part A, f of x is 8x to the 5th. That 8 is the constant c they were talking about before. If I want to find the derivative of this, the 8, when I take the derivative, the 8 doesn't go to 0 because it's not an 8 all alone. The derivative of this is 8 times. Now I take the derivative of x to the 5th. 5 multiplies out front. Take 1 away, I get 4 in the power. And so the derivative just turns out to be 40x to the 4th. Oops. So this just says if you have a constant, you can leave the constant there and take the derivative, and then multiply the constant times the derivative. Part B is similar. I'm going to rewrite this a little bit so it's easier to see what's happening, but that's negative 2/5 times x to the 11th, because that's x to the 11th over 1. So when I take the derivative of this thing, the negative 2/5 sits around. The derivative of x to the 11th, well, we take the 11 and multiply it out front. Then we take 1 away from the power. So there was 11, now it becomes 10. And now I can multiply that negative 2/5 by that to get negative 22/5 x to the 10. C is the same type of thing. To do problem C, part C, we have to rewrite f of x a little bit. I can't take the pi as a constant, 3.14. But I need to write the square root of x as x to the 1/2. But it's on the bottom, so to move it to the top, I have to make it the negative 1/2. Now when I find the derivative, the pi is a constant. Negative 1/2 multiplies out front, and I have to take 1 away from it. Well, when I take away 1 from negative 1/2, I get negative 1.5, which is negative 3/2. So the derivative turns out to be negative pi over 2 x to the negative 3/2. Perfectly acceptable way to write it. Although, let me write it a couple other ways as well. I could have also put that x to the negative 3 over 2 in the bottom and made it a positive 3 over 2. Well, you also could have written it in the bottom as the square root of x cubed. All of these completely acceptable ways to write the derivative. So this is what the constant multiple rule tells you. And let me just mention one more quick example of this to kind of to highlight the difference between these last two rules we've talked about. Let's look at a derivative that has both. 5x to the 3rd plus 6x squared minus 1. If I want to find the derivative, I can use the power rule. The 5 is a constant there. The derivative of x cubed is 3x squared. The 6 is a constant there. The derivative of x squared is 2x. The negative 1 has no x's by it, so the derivative of negative 1 is 0. So this works out to be 15x squared plus 12x. So you'll notice that if constants are in front of x's, they don't go away. But if it's all alone without an x, the derivative goes to 0. And there's another rule called the sum and difference rule, and this says that derivatives are very nice when you're adding and subtracting. With a derivative, if you're adding or subtracting two functions together and taking the derivative, you could just take the derivative of the two pieces. So what that means is derivatives distribute over plus and minus signs. And there's a proof of this in the book, but I just wanted to look at some examples. You could look at the proof. The proof is pretty straightforward. But I really would just like to look at some examples as to how this works. And we use this in the step above here. Notice 5x cubed, 6x squared, 1. These were all added or subtracted. And I took the derivative of each piece. That's what the sum and difference rule says. In A, when I look at h of x, I'm going to rewrite it so it's easier to use the power rule by writing the square root of x as x to the 1/2. Now to take the derivative of h of x, I just take the derivative of each piece around the minus sign. 3 times the derivative of x squared is 2x, minus 5 times the derivative of x to the 1/2 is 1/2 x to the negative 1/2. Now I did those kind of quickly, but you should make sure that you can get the same answers that I get with these. So now my derivative turns out to be 6x minus 5 over 2 x to the negative 1/2, which is okay. Or if you'd like, you could write this as 6x minus 5 over 2 square root of x. 2 multiplies by in front, take 1 away, you get x to the first. 1/2 multiplies in front, take 1 away, you get a negative 1/2. Part B, the same idea. There's a plus sign. I'm going to take the derivative of each piece around the plus sign. First I'm going to rewrite it so the x's appear on top with powers. The square root is x to the 1/2. Since it's on the bottom, I can write it on the top with a negative 1/2. X to the 4th over 2 is the same thing as 1/2 x to the 4th. Notice x to the 4th is over 1 there, so when I multiply those together, it becomes x to the 4th over 2. I can take the derivative around each piece. Negative 1/2 times 2, so I have 2 times negative 1/2 x. When I take 1 away, I get negative 3/2. Plus 1/2, 4x to the 3rd. So the derivative, 2 times negative 1/2 is negative 1, x to the negative 3/2. 1/2 times 4 is 2x cubed. A perfectly acceptable answer, or if you'd like, you could have written that as negative 1 over the square root of x cubed plus 2x cubed. But both of those are acceptable answers. But notice when I'm using the sum and difference property, that just means you can take the derivative around plus and minus signs. Well, now we have to talk about Euler's number. Euler's number is the base of the natural log function. Euler's number is approximately equal to 2.718. And the natural exponential function is e to the x, or 2.718 to the x power. About. Euler's number actually is irrational, so you can't write it down. That's why we use the funny picture, the e, to represent it, just like pi. But the reason I call it the natural exponential function is because the derivative of e to the x is just e to the x, which is a really nice thing. So if f of x is 3 e to the x, then the derivative would be, well, 3 is a constant. The derivative of e to the x is e to the x. Exact same thing. If f of x is 1/2 e to the x plus 3, then the derivative of this would be 1/2 is a constant. E to the x, when I take the derivative, gives me e to the x. The derivative of 3 is 0. just 1/2 e to the x would be the derivative of that. So when you take derivatives with e to the x, you just get e to the x back. It's a really, really nice thing about the function e to the x. So this is something we'll be using more often later, but I just wanted to talk about it because the book does here. Equations of tangent lines. The derivative, the whole purpose of a derivative is to get us the slope of a tangent line. That's what the derivative does. It gives you the slope of the tangent line at a point. And so to come up with an equation of a tangent line, remember the tangent line we talked about before? It's the line that just touches the graph at a certain point, but it moves in the same direction. So for example, if I had a function that looked like this, the tangent line right here at x equals a would be this straight line there. It points in the direction that the graph is moving there, but it just touches the graph in one spot. So that tangent line is if you were spinning a rock around and you release the rock right at that point. It's the straight line the rock would fly off in. We're just moving in the direction of the curve. But if I wanted to find the equation of this red line here, this red straight line is a tangent line. Well, I have to use the line equation. Y minus y1 equals mx minus x1. The easiest way to write a line equation is to use the point-slope form. That's what that's called. So with the point-slope form, you leave the x and the y in there because they generate your equation for a line. Y equals. But the x1, y1 is the point on the graph where the tangent line touches it. So the x1 is that point A on the x-axis, and y1 is the y value that goes with that point A. And to find the slope of the tangent line, I got to figure out the derivative at A, because the derivative tells me the slope of the tangent line. And so that's what we have here. To find the equation of a tangent line, 2f of x at x equals A. So f of x would be the graph, and this line here is the tangent line. But x1 in the formula here, x1 you can see up above in the equation of the line, there's x1. That's A. It's the given x value. y1 is the y value at A. So to find y1, I take A and I plug it into the function. It's the y value at A. And m is the derivative at A, because the slope of the tangent line is found from the derivative. So we're going to draw some line equations for these functions here, and we're going to use these 3 steps. So you'll need to know this equation of a line for the rest of the semester, so it's good to get it down now. Y minus y1 equals mx minus x1. You could also use y equals mx plus b. That's just a little bit harder to work with when writing the equations, but I'm okay with it if you want to use that one. I'm going to be using the point-slope form, though, and I'm going to find the derivative of the equation of the tangent line for these. So let's do the first example here, example A. Let's just find the equation of the tangent line to negative 3x squared plus 2 at a equals 1. And here is my line equation, y minus y1 equals mx minus x1. And I know that my x1 is the given x value, which is 1. And if I want to find y1 in the formula above here, if I want to find y1, I have to take 1 and plug it into the function, because the function gives me the y value. And when I do that, I get negative 1. Negative 3 plus 2 is negative 1. So the y value is negative 1, the x1 value is 1. To find the slope of the tangent line, I find the derivative, and I plug 1 into that. So to find the slope of the tangent line, this is the derivative at 1. Well, I have to find the derivative to do this. Negative 3 times x squared. The derivative of 2 is 0, so the derivative is negative 6x. When I plug 1 into that, I get negative 6 times 1, which is negative 6. This is my slope. So now I can write the equation. The equation is y minus my y1. Well, let me rewrite this thing. The equation will be y minus my y1 is the point -1 equals my m, the slope, is -6. And my x1 is the given value at the very beginning of the problem, is the place where they told me this was starting at. My x1 turns out to be x equals 1. So the equation of the tangent line can be given by y plus 1 equals -6 x minus 1. I have no problems with you leaving it in point-slope form. However, you also could have written it in slope-intercept form, and that would have been y equals -6 x plus 5. So I'd have taken either one of those for the equation of the tangent line. But notice I'm perfectly fine with the point-slope form. If you solve this for y, you get the slope-intercept form, which in this case is -6x plus 5. Rewrite it so it's easier to see. Let's try that with b. For part b, if I want to solve part b, I need to fill in the same equation because I'm looking for the tangent line. Y minus y1 equals m, x minus x1. x1 is that given value of a, and here a is 0. To find y1 in this equation, I need the y value at x equals 0, and so I plug 0 into the function. E to the 0 over 4 minus 0. E to the 0 is 1, so the y value is 1/4. To find the slope m, I need to find the derivative at the given x value is 0. Well, to find the derivative, I'm going to rewrite e to the x over 4 as 1/4 e to the x. So to find the derivative now, 1/4 is a constant. The derivative of e to the x is e to the x. When I take the derivative of x, this is really x to the first. So I multiply the 1 out front, and the power goes x to the 0. 1 gets multiplied out front, and then when I take 1 away from the power, I get 0. So this 1 gets multiplied out front. When I take 1 away from the power, I get 0. And x to the 0 power is 1. So this is 1/4 e to the x minus 1, because x to the 0 power is just the number 1. So to find my equation for the tangent line, I need to take the a value, which was 0, the x value, which was 0, and plug it in for x. E to the 0 is 1, so I have 1/4 minus 1, which is -3/4. That's my slope. So now I can write the equation of the tangent line. The equation of the tangent line is y minus my y1 value is what I got when I plugged 0 into the original function. y1 is 1/4. And that equals m. M is my slope. My slope is -3/4. X minus x1. Well, my x value, the x value I started with, was 0. So I get y minus 1/4 equals -3/4 x, which is the point slope form, which is completely acceptable. Or if you solve this and you want to write it in slope-intercept form, you get y equals -3/4 x plus 1/4. Both of those are perfectly acceptable equations for me. Point slope, slope-intercept, point slope, slope-intercept. Either one would work. So there's the idea. Y minus y1 equals m, x minus x1. Our given value is x. Plug it into the function for y. plug it into the derivative for n. And those are the equations to those tangent lines. You can also use this to find places where a certain graph has a slope that's the value that you want, because the slope of the graph matches the tangent line at that point. So for this problem here, to figure out where the slope of the curve is 0, I just take the derivative, because the derivative tells me the slope of the curve. So to figure out where the slope of the curve is 0, I take the derivative of the curve. In this case, it's 3t squared minus 27. That's the derivative. 3t squared minus 27 tells me equals the slope of the curve, equals the slope of the tangent line. Well, I want to figure out where the slope of the curve, where the slope of the tangent line is 0. I want to figure out where the derivative is 0. So this leads me to solve 3t squared minus 27 equals 0, because the slope is 0, and 3t squared minus 27 is the equation for the slope. So to solve this, I can add 27 to both sides. I can divide by 3. And I can take the plus or minus square root. So the places where the curve is 0 is plus 3 and minus 3. Now notice if I plug plus or minus 3 into the function, I don't get 0. But if I plug plus or minus 3 into the derivative, I do get 0. The slope of the curve is the slope of the tangent line, is the derivative. So if the slope of the curve is 0, if the slope of the curve is equal to 0, then the derivative is equal to 0. So those are other ways that we can use slopes of tangent lines. And there's one more topic here in this section, and it has to do with higher order derivatives and the notations they use. The first derivative is f prime of x, or d over dx of f of x. The second derivative is f double prime of x, although if they write it with the other notation, it's d squared f over dx squared. Or you could think of the second derivative as the derivative of the first derivative. These are just different ways that they write the derivatives. A lot of times the first way is used most often. And if it's any number, the nth derivative, we can write f prime and f double prime. But when we take derivatives bigger than 2 or 3, usually they put the derivative as a number in parentheses, f to the n of x, the nth derivative. Or dn of f over dx to the n. Probably write it right. Or the derivative of the function before. So this is stuff that you've already learned. It's more like the notation of it. For example, 5x to the 4th plus 10x cubed plus 3x plus 6. And they want me to find the first, second, third, fourth, fifth, and sixth derivative. So to do this, I just keep taking derivatives of the ones before. So the f of x is 5x to the 4th plus 10x cubed plus 3x plus 6. I can find the first derivative with the power rule. I have 20 x to the 3rd plus 30 x squared. The derivative of 3x is 3. The derivative of 6 is 0. And you should check that you can calculate that derivative. F double prime is the second derivative, so it's the derivative of the first derivative. 20 times 3 is 60 x squared. 30 times 2 is 60, becomes x to the first. The derivative of 3 is 0. 3 times 20 is 60, take 1 away from the power. 2 times 30 is 60, take 1 away from the power. The derivative of 3 is 0. The third derivative, notice we write a little 3 now because the primes get hard to read. 2 times 60 is 120, take 1 away from the power, you get x to the first. 1 times 60 is 60, take 1 away from the power, you get x to the 0 power, which just gives me 1. That's how that stays 60. The fourth derivative, take the derivative again. The derivative of 120x is 120. The derivative of 60 is 0. We can find the fifth derivative. That's the derivative of 120. Well, 120 is a constant. There's no letters by it. So the derivative of 120 is 0. A lot of times people say, oh, well, you can't find any more derivatives now because you got a 0. That's not true. 0 is a constant just like 120 is. So when I take the derivative of a constant, I get 0. 0 is a constant. So when I take the derivative of 0, I get 0. And notice, from the fifth derivative down, it's just going to stay 0 forever. And with polynomials like this, that happens. At a certain point, the derivative goes to 0. But notice the notation that I'm using to describe these derivatives. These derivatives, the power rule makes it a lot easier to find. You can take the derivative around plus and minus signs. You can leave constants in front of functions. But if it's just a constant all alone, the derivative turns out to be 0.